Alright, so let's work through a strong acid, strong base titration together. 3.0 times 10 milliliters would be 30 milliliters, just with 2 sig figs, of 0.5 molar HCl, and it was titrated with 0.5 molar sodium hydroxide. So in this case, we do know the concentrations of both. We're just looking at it in order to get kind of some practice with the process. And we know that the reaction between a strong acid and strong base is a neutralization reaction because it produces a neutral product, unlike a weak acid, weak base reaction, where we wind up with a pH that is not equal to 7. In this case, we're just producing water. Water is neutral. And we're going to be doing 4 different things with this process. So for the first one, we're just going to find the initial pH of the hydrochloric acid. And this is pretty easy. It's just going to be the negative log of 0.5, which means that we have a pH fairly low of 0.30. And this is because it is a strong acid, hydrochloric acid, which means 100% dissociation, which means it's just the negative log of the concentration. Alright, now we want to know what the pH is after 15 milliliters of sodium hydroxide has been added. Alright, so if we have a 0.030 liter solution of HCl, okay, so that's just 30 milliliters, and there is 0.50 moles for every 1 liter of solution, that means we have 0.015 moles of HCl or H+, because that's the player we're concerned with. And then we are adding to that 15 milliliters of sodium hydroxide. And so the 15 milliliters, 0.5 molar, we're going to produce 0.0075 moles of sodium hydroxide, or just what we're concerned with would be the hydroxides. Alright, so now we know the moles of both of those. Let's get them out of our way. And then to do the rest of it, an ICF or an ice table without equilibrium would be a good place to go. So the reaction we're concerned with is H plus OH minus, yielding water. And so in this reaction, we would have 0.015 moles of H plus, 0.0075 moles of hydroxide, initially no water. And so then if we look at this, we've got a smaller concentration of OH minus, so we know that's going to run out first. And so this is going to decrease by 0.0075, which means that this one would decrease by 0.0075. And so then in the end we would have 0 hydroxides left, and we would only have 0.0075 of the H pluses, so it'll cut it in half. Of course, we could figure out what the water is. We're looking for that. We just want to know what the pH is, so all we really need to know is the H+. And now that we know that the H+ concentration is 0.0075, we can get the pH. However, 0.0075 is the number of moles. For pH, we need to know the molarity. So we don't go with the original volume, okay, of the HCl, which was 30 milliliters. Now that we've added 15 milliliters of sodium hydroxide, the new volume would be 45 milliliters, which means we're going to take that 0.0075 and we're going to divide it by 0.045 or 45 milliliters. And that will give us a concentration then of 0.17 molar. And so the negative log of 0.17 molar means that the final pH is going to be 0.77. Okay, for part B, at this point we have used 30 milliliters of sodium hydroxide, and we started with 30 milliliters of HCl, and they both have the exact same concentration of 0.5 molar. And so if we've added equal amounts of equal molar, that means we're going to have a concentration of H plus that is equal to the concentration of OH minus. Since this is a strong acid, strong base titration, this is the equivalence point, it's also the end point, and that means the pH is going to equal 7. Now, where this is different than titrations involving either weak acids or weak bases is the spectators in this reaction, and so that's going to be the Na plus and the Cl minus, which we haven't talked about because they are just spectators. They do not affect the pH. Therefore, at the equivalence point when these two are equal, the pH will be 7 because neither one of these guys is going to hurt it. So now would be a good time to pause the video and see if you can figure out D on your own. So try it out and then resume the video and I'll just show the answers. Alright, so for this one we have our original 30 milliliters of 0.5 molar, which we already figured out was 0.015 moles of H+, and now we have 45 milliliters of sodium hydroxide, which would be 0.023 moles. So then, at the end, after we've mixed those two together, this is the smaller number, which means it's going to get used up first. And so we would wind up with 0 H pluses. So now we're going to enter into the basic range, because if we have more OH minuses, not enough H pluses to cancel it out, we're going to wind up with some extra hydroxide at the end. We're going to have 0.008 moles. So now that we've added 30 milliliters of HCl and 45 milliliters of NaOH, that is 75 milliliters, which means we have 0.1 molar hydroxide. Take the negative log of that to get the POH, subtract it from 14 to get the pH, and find out the pH of this solution now is 13. So we've added extra over the sodium hydroxide, which is going to make the solution basic. So if we were to do a graph of pH versus the volume of sodium hydroxide added, for that example we just did, we would start off with a pH that is much, much less than 7, so this would be just the acid inside of that beaker at the bottom, or flask at the bottom. As we slowly add that sodium hydroxide, you saw that the pH didn't change all that much. We went from, 0.3 to 0.7 as we added it, and then we hit that point where we added the equivalence, and it jumped up to 7. And so this is a very, very distinct titration curve, where we have a very, very slow increase, but then suddenly, it shoots up to the equivalence point and actually beyond the equivalence point. And then it comes up here, and so once we've added only an extra 15 milliliters, we've now shot up to the pH of 13 range, and then it just slowly increases from there. But this intersection right here between each of the spikes, so between the top end or the bottom end and the top end, would be the equivalence point, so the midpoint in between those. And we see right here that the midpoint happens to fall on 7. And so this would be a strong acid, strong base titration then, because the equivalence point is right on a pH of 7, the end point. So be ready to recognize titration curves that aren't going to be labeled as what they are. You need to look at this one and say, okay, this would be a strong acid, strong base, because the equivalence or end point is right on 7. We have a steady increase, a sharp spike, and then a slow, steady increase. And just to kind of give you an idea, this change right here isn't any more than about 1.5 in pH. And then suddenly right here, it jumps all the way up to the basic range. So the change in pH is very, very large in the vicinity of the equivalence point. So once we get there, it just shoots up. That's why we got to be very, very steady and careful with a titration. Okay, so here's an example of a mystery question. So we have 31.25 milliliters of 0.25 molar HCl, and it was titrated to the end point with an unknown concentration of sodium hydroxide. So we don't know what the concentration of our sodium hydroxide is. We want to figure that out. So we use our burette, we open it up, we get it to the end point, and at that point we have added 32.75 milliliters from our burette. We want to find the concentration of the titrant, so the stuff that was in the burette, the sodium hydroxide. So originally in our sample, our known sample, we have 7.81 times 10 to the negative third moles of H+. So we know what that concentration is, and since we're going to the equivalence point, the end point, this is a strong acid, strong base, we know that at that point, the concentration of H+ has to be equal to the concentration of OH-. So then that means after 32.75 milliliters of sodium hydroxide had been added, the H+ now equals the OH-, which means in that sample right there, there had to have been that many hydroxides. So if we added 7.81 times 10 to the negative third moles of H+, we had that many moles of OH- at the equivalence point. And so if we're going back and trying to figure out what the concentration of our original sample was, there was that many moles of hydroxide in 32.75 milliliters of sodium hydroxide. So that means the concentration of our original sample would have been 0.238 molar.